AP Chem Unit 1.5, Atomic Structure and Electron Configurations. So when we're talking about the structure of an atom, we have a Bohr model here, and our red little dots are going to be orbiting around our nucleus, and those are going to be my electrons. My charge for my electrons is going to be defined as -1, and my mass is 1/1836 of an AMU, basically 0. My protons are going to have a defined charge of +1 and then a mass of approximately 1 AMU. And my neutrons are neutral and they have a mass of 1 AMU. Coulomb's law is going to be the main focus for a lot of the interactions that we're going to see within the periodic table and within each atom. And Coulomb's law is going to calculate the force of attraction between charged particles. This is Coulomb's law. So force is going to be proportional to the charge of particle 1 times charge of particle 2 divided by the radius and those distance between those charged particles squared. And we can have Coulomb's law be a force of attraction or a force of repulsion, depending on the charges. So remember that like charges repel and unlike charges are going to attract. And my distance between the centers of both of the charged particles is going to be defined as my R. Q1 is going to be my electrical charge for the first particle of interest. Q2 is my electrical charge for particle 2. And again, R is going to be the distance between those particles. And again, we can have a force of repulsion if the charges are like charges. The main takeaways for any Coulombic problem is going to be that the larger the charge differential, the larger the force is going to be. So if I'm dealing with small charges, +1, +1, -1, etc., that's going to be a lot smaller of an attraction differential than where we have larger charges such as +4, -2, etc. And the larger the distance between the particles, the smaller the force. Remember that the distance is going to be the dividing factor here, and then it is also squared. So if this R value is larger, then we are very much decreasing the amount of overall force that we are experiencing. The first thing that we're going to see Coulomb take hold of is going to be ionization energy. And Coulomb's law can be used to predict the amount of energy required to remove an electron from an atom. Okay, and this is really the only qualitative application that we need for the AP exam. And the things that you need to know are that the electrons that are further from the nucleus are going to be easier to remove. Remember again that for Coulomb, the R value, the distance between the particles of interest, is going to be the dividing factor and is also going to be squared. So if my electrons that are on my valence shell, those are going to be further away from the positive nucleus. That is, we're comparing to where we're feeling the force of attraction there, and as we get farther away, my attraction is less, the force of attraction is less, and therefore it is going to be easier to steal those electrons versus the electrons that are in the inner shell, where we are much closer to the positively charged nucleus, and those are going to require substantially more energy to remove. The distance does have a much larger effect on ionization energy than shielding does. So shielding is the idea that we have basically electrons that are getting in the way and are kind of buffering between the outer electrons and the nucleus in terms of like the pure amount of charge that they are attracted to. but since distance is squared, it is going to be the thing that has the larger effect overall. So the ionization energies for period 3, you can see that as I go from left to right, as I increase my number of protons inside of my nucleus, I am also going to be increasing my ionization energy as the overall trend. Now we do have a small bump down here where we go from phosphorus to sulfur. This is the first double up electron, so we have a little bit of electron repulsion here that makes it just ever so slightly easier to remove the very first electron from sulfur than it would be from phosphorus, but my overall trend is the main thing that I am most interested in. And we can see that as I go from left to right, as I increase my number of protons in the nucleus, pulling on the same shell, I am increasing my ionization energy. So again, the increasing number of protons is going to be the thing that allows me to increase my ionization energy as I go from left to right across a period. And for period 3, the second ionization energies, you can see that we have some interesting things going on here. So sodium only has one valence electron. So its second ionization energy, we are now stealing from inner electrons. So we have a major jump up from what we had before. Whereas with magnesium, magnesium has two valence electrons, and so the second ionization energy, the second electron that is being stolen, is still from that valence shell, and so it is much easier to take than an electron that was originally within the inner shell. And you can see that across the period. The second ionization energy is higher than the first ionization energy because, again, once we remove that first electron, you now have a higher positive charge attracting less electrons. And so those Coulombic attractions are going to be able to pull those electrons in tighter. And as they come tighter and closer to the nucleus, they are more difficult to steal, and therefore your second electron is harder to steal than your first. So as we look at this example problem, which states which electron would be easiest to remove, we have 3 examples here. We have charge differentials where we have 2 plus and 1 minus, a plus and a minus, and then we have a difference differential between plus and minus. So you can think of these positives as our nucleus and these negatives as our electrons. Again, we are going to be most concerned with the distance, and that will be our determining factor. So between A and B, we can see that A is going to be more difficult than B because we have a larger charge differential, and those are being multiplied together. The difference between B and C is going to be the difference differential, and so according to Coulomb's law, the force of attraction is going to be proportional to the magnitude of the charge on the particle and inversely proportional to the distance between them. So picture C has the lowest magnitude of charges. We just have 1 positive and 1 negative. And we also have the largest distance between those 2 charged particles. And as such, those particles are going to be less attracted to each other. We have a smaller force of attraction, and therefore it will be the easiest to remove. Next thing that we need to consider is going to be electron configurations. So this is a periodic table where we have the different shells, the different orbitals broken down, where we have our s electrons, d, p, and f. As a reminder, your s shell can only hold 2 electrons, your p shell can hold 6, d can hold 10, f can hold 14. And each arrow represents a single electron as either spin up or spin down. And we have to fill those electrons in an appropriate order. And that order is going to follow 3 main rules. The first rule is going to be Hund's rule. So Hund's rule states that electrons must occupy empty orbitals first before double occupying them. So that means that we are going to avoid sitting next to another electron. Remember that electrons have a like charge, which means that they are repulsed from each other, and so they are not going to want to fill the same orbital, the same box. So you are going to fill each box individually before you ever double up a box. The next principle is going to be the Aufbau principle. The Aufbau principle states that electrons must occupy orbitals in order of increasing energy. We have to go in order. We have to go 1s, then 2s, then 2p. If we go out of order, those electrons don't have the energy it takes to actually maintain that space, and they will fall back to their appropriate order. And the last thing is going to be the Pauli exclusion principle, which states that electron spins must be opposite within the same orbital. So within the same box, those electrons are going to be facing away from each other. They do not like each other, and they are going to look away, not in the same direction, not towards each other at all. So for an example of electron configurations, we're going to do the orbital notation for chromium. So chromium going to be element number 24, which means we need 24 total arrows, total electrons to be in our electron configuration. And first up, we are going to be dealing with the first and second electrons. They are in energy level 1, and they are in the S block. So we are going to have 1s, and we have both of those electrons present, and so we are going to have an up arrow and a down arrow. My third and fourth electrons are going to live in energy level 2, still the S block. And so I will have spin up and spin down. Electrons 5 through 10 live in the 2p block, and then I'm going to have 3 total orbitals with 6 total arrows within. And my 11th and 12th electrons live in the 1, 2, 3rd energy level. This is the S block, and I have 2 of them, so 3s and then 2 electrons. Electrons 13 through 18 are going to live in the 3p block. And again, the p block has 3 orbitals, 3 boxes there, and since I have all 6 electrons accounted for, I am going to have 6 total arrows present. The 19th and 20th electrons live in the 4s block, and they are both present there, so I'm going to have my 4s block filled. And then finally, I've gotten to where my very last electron is, the 24th electron. I have 1, 2, 3, 4 electrons present within the 3d block. Remember that the d block is undesirable. It's going to drop down a single energy level. And so even though this is the 4th row, this is the 3rd energy level, so 3d, and then I have 1, 2, 3, 4. None of those electrons are going to want to room together, and the d block still contains a grand total of 5 orbitals, even though I only have 4 electrons living within them. The shorthand configuration for chromium, we're basically doing the same thing, except for instead of drawing out the electrons, we're going to just state how many are present. So 1s, I have 2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. As a general note for speed, for shorthand notation, everything should be completely maxed out. Again, S maxes out at 2, P maxes out at 6, D maxes out at 10, and F maxes out at 14. Everything should be maxed out except for the very last energy level here. So we had 24 electrons. So just the 3D block was the only thing that could possibly be anything other than the max occupancy level. So that's shorthand, and then the last type of electron configuration notation is going to be noble gas notation. Noble gas notation, you're simply going to backtrack to the last perfect electron configuration. So the last perfect electron configuration, the last perfect element before chromium was argon. So we can say, hey, you remember argon's configuration? It was perfect. So nice. I don't want to say it again. And we can just go ahead and state argon. And then any electrons that argon does not have. So argon The bracket, argon bracket, is going to take place of the electrons 1 through 18, and then I only need to account for electrons 19 through 24. 19 and 20 live in 4s, and I have 2 of them, so 4s2. And then 21 through 24 live in 3d, and I have 4 of them, so 3d4.